Hello, AP Calculus students. This lesson is a kind of strange one. It doesn't really fit into our curriculum of like lesson 2.1 or 2.7 or something. I really designed this lesson to be viewed kind of after you've tested on topic 2, derivative rules and tangent lines, or maybe you're prepping for a test and you're still a little bit unsure of how to do derivative rules and tangent lines. So this video assumes that you know the general idea of a tangent line, though I will reteach it. And then it also assumes you're pretty comfortable with your derivative rules. So if there's something I go over here and you're not quite sure about it, you might want to pop back to a couple other topic 2 videos. But without further ado, let's get into it. We are going to kind of build up how we write tangent lines in calculus. And writing tangent lines at first, you're like, well, I don't really care. Why does it matter that a tangent line bounces off a graph at one point? And that's actually not quite what it does, but we'll go more into that in just a bit. And the reason why is it's really a bridge to something called infinite series. And we're going to get to that in Calc BC or Calc 2, but the idea of tangent lines is it's giving you the ability to approximate answers of a function that might be really tough to do without a calculator. For example, it gives you the ability to recreate the sine function or the natural log function without using sine or natural log. It uses pretty nice numbers. And we'll see that as we move through here. Now, that's not always the case, and there are a few problems that I chose that aren't going to have great numbers, but I think once you get the general idea of what you're doing, you should be pretty confident with tangent lines. So I split this video into 4 parts. The first part is a pre-calculus topic. It's how to write the equations of secant lines, or really just lines for the most part. And then parts 2, 3, and 4 are writing tangent lines, and they're from our usual 3 perspectives. We're going to write a tangent line using equations, using graphs, and using a table. No real-world examples so far. So let's go ahead and start with how to write the equation of a line. Now, you've probably learned many equations of a line. Probably the 3 most common are slope-intercept form, which is that y equals m times x plus b, your hk form, which is m parentheses x minus h plus k, and then standard form, which we don't do as much anymore, but it actually shows up a lot both in real-world problems and strangely in higher dimensional calculus. It tends to be a little bit easier to write a form of a line a times x plus b times y equals c, where a, b, and c are all constants. Now, that's really the last time I'm going to mention standard form today, but we are going to talk a little bit more about slope-intercept form and HK, or translation form. Now, on the AP exam, you can write the equation of your tangent line in any form you want, as long as if you type it into Desmos or a graphing calculator, it makes the correct line. You won't see many standard forms. You'll see a decent number of slope-intercept forms, but I'd argue that generally this translation form comes up the most. Now, sometimes you'll see this written in a few different ways. You might have had it introduced as point slope form, y minus y1 equals m times x minus x1. Hopefully you can see that's the same if you just add y1 over to the other side. I like HK form because y is already isolated. You might even see kind of a slightly different version of this where you see y equals k plus m times x minus h. And actually there's a reason that your teachers might show it to you that way, and that's really prepping you for what you're going to do with those infinite series in Calc 2 and Calc BC. But either way, all of these are equivalent forms of a line. I really prefer to write my equation in HK form. HK form just allows you to pick HK, which is any point on a line, and the slope, and you're done. As opposed to slope-intercept form, where it's the slope, but then b is not any point on the line. B is the y-intercept, and it's not too often that we actually have the y-intercept. So what I'm going to show you here is generally starting with HK form, and then I'll show you how to convert it to slope-intercept form. There are, of course, other ways to write slope-intercept form, but I think this way is pretty straightforward. By the way, if you hear some background noise, it is crazy windy at my house right now. It's like 40-mile-an-hour winds out there, so it's probably getting through the windows into my mic, but that's okay. So let's go ahead and get started. Given a line with a slope m equals -2, which passes through the point 3, 5, write the equation of a line in both HK form and slope-intercept form. All right, well, let's start with HK form, right? It's that same y equals m. They told us m was -2, x minus h plus k. Now, you're probably used to seeing this where the h value is just always the opposite, and that is true, and that's it, you're done. Now, if you wanted to write this in slope-intercept form, you just distribute the slope, nothing terrible, and finish it off by combining like terms. And look, we've got something in slope-intercept form as well. So pick your favorite, but do know that on the AP exam, if you start off with the right answer like this guy, and then you make a mistake multiplying, maybe you keep this as a negative instead of a positive, and so you were to get -1 instead of +11, even though you got the right answer, if you converted it because it made you happy to present it in a different form, you actually would lose the entire answer point. So even though you got the right answer because you stated this is your right one at the end, that would be a no-go. So I really suggest that as soon as you have any right form of the answer, just stop there. But for you, I can't call you perfectionists, but those of you that love slope-intercept form, maybe purists, it is okay to convert if you'd like. Okay, let's try another. Find the equation of the line which passes through 2 points, and that's all they gave us. That's frustrating. Well, I think the first thing we need, of course, is the slope, and we know our usual slope formula. Let's zoom in here. Maybe. There we go. I always, and I teach Algebra 1 students as well, I always make them write the parentheses first, and so I think I've just started writing the parentheses as well. You don't have to, but I find that I make fewer mistakes this way with negatives. Okay, y2, y1, x2, x1, and of course either order is fine. You could have done y1 minus y2, but I imagine you guys know that. Let's see, -2 plus 3 is +1, -5 plus 1 is -4. Cool. And write your slope however you'd want. I think most commonly people would move the negative to the middle. We know we can put it on the top, but we can't put it on both. And then we finish with, of course, the equation of our line. Y equals, we have our slope now, and then we have x minus h. Well, wait, we have 2 points here. Well, we know it doesn't matter. I'm just going to pick the first one. So we have x minus, and then h here is -1 plus k. And that would be okay for an answer. I imagine you guys would have simplified that in your head and just said x plus 1 minus 3. So I like this one a little bit more. But you can also see that that's why in HK form you do the opposite, right? Because it's always minus. We put a minus in here, it becomes a positive, nothing terrible. And our last one. Right, the equation of the secant line. That's the first time we've really introduced that in these problems, and we're going to dive into that a little bit more, which passes through the given graph at -1, comma f of -1. Maybe I should label that down here as this -1, comma f of -1, and 2, comma f of 2. There we go. Nice. So we need to talk about the difference between a secant line and a tangent line. And the idea behind a secant line is it is created using 2 points on a graph. I bet you can see which 2 points is creating this secant line, right? -1, comma, this one looks to be -3 down here. Rewrite that. And then the one in green, we of course have 2, comma, +3. We're using these 2 points to create a line. Okay, so if I even wanted to kind of eyeball this line up here, you can kind of like approximate the slope. It looks like it's up 2/1. There we go. Okay. There is my secant line. Now, we don't want to think of a secant line as only passing through 2 points, because if you follow this line through, it does cross the initial graph 3 times. That's not what a secant line is. A secant line is created using 2 points. Okay. Now, how do you create it using 2 points? Well, the first thing we do is find the slope between the 2 points, but I would argue I actually found the slope just by counting, which is often more efficient. So I'm pretty confident my slope is up 2/1, which is 2. If not, we would have gone our old route over here. And then it's using HK form. Now, HK form only uses one of those 2 points, 2, and then we have something like x plus 1 minus 3. I just use the point up here. And we should be set, right? Now, if you wanted to convert, or in fact, I don't even think I need to convert. We know that the slope is here, and we even have the y-intercept this time. It's -1. That's not too bad. So either of these forms would have been pretty quick. But again, to find a secant line, the first thing you need to do is find the slope between those 2 points. And I was able to count the slope. You might have to use the slope formula. But that is a contrast to actually doing calculus, right? So we didn't use any calculus on that previous page. I tell my students at this point in time, you only know 3 calculus concepts. You know limits, which is really only the first unit. We don't use them much throughout the rest of the year, so not on this at all. Derivatives, or a theorem. We're not going to do any theorems today either. So let's go ahead and focus on the main theme for this semester, which is taking a derivative. Now, I know there are still some of you who are like, what is a derivative? I don't get it. Well, a derivative is going to have those 2 different notations. You'll either see it as dy dx or y prime. Those mean, for all intents and purposes, the same thing. The derivative measures the slope at a single point on a graph. Now, I really like to think of slope as steepness. I know a lot of mathematicians will cringe and say you can't really measure the slope of a graph. I'd argue it can. I mean, the slope is just the steepness, but a lot of times they'll say the instantaneous rate of change, which is really just a fast way to say how steep is the graph, right? So if we were thinking back on the previous page and we picked a point here, maybe I'll pick this point right here on the graph, and I would just say, how steep is this? Well, I know that it's certainly going up at that part. So is it going up 2 over 1, up 2.5, up 7, up 10 over 1? I'm not sure. A derivative will tell us exactly how steep it is there. Okay. Now, jumping back here, the idea of the slope of a line is really easy because a line is the exact same steepness no matter where you're standing, right? If you're standing down here on a line versus somebody that's standing up here, it's the exact same steepness. If the steepness down here is up 2 over 1, the steepness up here is up 2 over 1. But most other graphs, the steepness is not constant, right? Going back to that same example, I had a steepness here. If I compared it to the steepness over here, they are clearly not the same. This is a negative steepness, this is a positive. And so calculus becomes really useful in measuring how steep a graph is. Now, I didn't give you any real-world examples here, but if you're measuring the steepness, you're measuring how fast something changes. And if you can measure the speed or the rate of change of anything in the world using calculus, it becomes a lot more useful. So let's go ahead and talk about those tangent lines for now. Now, I mentioned I like HK form, but with calculus notation, we're going to notate this just a little bit differently. I tend to call my tangent line t of x because I'm very creative, t for tangent. And then we have those same 3 pieces, right? We have our m times x minus h plus k, where you will see these 3 pieces as a being the x value. Oftentimes that's given. I'd say about 90% of the time they will give you the x value. F of a is going to be the y value. You'll usually have to find this. And then f prime of a is almost never given. Say almost never. And you'll certainly have to find this. So what is f prime of a? Right, f prime of a is the, and you're going to probably need 2 lines here. It's the derivative function. And now, it's not just the derivative function, because the derivative function, it could say, like, take the derivative of x squared plus 2x. And you're like, ooh, that's 2x plus 2. But that's not our slope, because f prime of a is the derivative function evaluated at x equals a. So there's 2 steps to find this. The first step is take or find the derivative function, and then the second step is substitute in x equals a to find a value for the slope. Right, on the previous pages we had numbers for this slope, and it's not going to change when we do tangent lines. So let's go ahead and try a few. Write the equation of the tangent line to y equals that at x equals negative 1. Alright, so here's how we're going to go ahead and start. We know we are working towards, and I'm going to kind of put this down at the bottom, we're working towards 3 items. We are going to need the derivative function evaluated where? Oh, that's right, negative 1. And then in HK form, that's going to be x minus, and then what's our h value? Oh, it's negative 1, so I'll change that to a positive 1. And then plus f of, Oh, yep, negative 1. So again, I'm taking the x value and filling it into my formula. Now to do that, and I probably should have left myself more space, I'll just kind of do it right up above, we'll have this guy right here with 2 extra values missing. Let's find each one. F of negative 1 doesn't seem too terrible. F of negative 1 is just take our equation, maybe I'll call it f of x so it's a little more clear, and replace all the x's with negative 1. Now, I know many of you are reaching for your calculator right now. I'd really suggest that you don't do that. You should really force yourself to do more mental math, right? About 2/3 of the AP exam doesn't allow a calculator, and you really can't afford to lose those extra minutes of like, wait, how do I do negative 1 cubed without a calculator? Do I need parentheses? You really should practice it. Use your calculator at the end to check it, but the more you practice, the better you perform. So negative 1 cubed, negative 1 squared, 2 times negative 1, and minus 5. So this will give us 0, 2 minus 5. I'm looking at f of negative 1 being negative 3, which means I can fill in my ending part at negative 3. Last but not least, we need to find f prime of negative 1. But this is saying substitute negative 1 into the function called f prime. We don't have an f prime function yet. We should probably find that. Again, at this stage, you should know how to find the derivative. 3 comes down, 2 comes down, drop the x, negative 5 becomes 0. And then we find f prime of negative 1. Same thing, challenge yourself to do some mental math. I don't think it's too scary here. 1 times 3 is 3, minus 2, that's 3 minus 4, or negative 1. And there we go, we have a tangent line. Now, this tangent line was actually, I think, pretty cleverly designed by me because it uses an equation that we saw on the previous page. And so I'm going to show you just a real quick way that I can check this. I'm going to take this equation, which passes through the point negative 1, negative 3, and has a slope of down 1 over 1. So we jump back here, negative 1, negative 3, oh, that is coincidentally this point right here. And if we follow out the slope of down 1, right 1, down 1, right 1, or reverse it, okay, we see that we have this line coming through here that bounces off our graph. Now, I mentioned that a secant line doesn't mean it only crosses a function in 2 places. The same way a tangent line doesn't mean that it only touches the function in 1 spot, right? It actually crosses or intersects in 2 different places. It's still a tangent line. The reason it is tangent is actually twofold. First, they share a point, negative 1, negative 3, and they share the same steepness. They share the same slope. So now that I know that the slope of this tangent line is negative 1, then I can also say the slope, f prime, right, of negative 1 of the graph is also negative 1. They happen to be the same number. So remembering that a tangent line shares the slope and the point will come into play in just a bit. All right, let's look at a few more, and I don't have graphs prepped for all of these, but I do for the second one just for fun. So write the equation of the line tangent to f of x equals all that. I'm just going to leave some blanks down below. Okay, and it's at 3 pi over 4, so we might as well fill that guy in too. And it's the same steps. Let's find the y value first, f of 3 pi over 4. You should know your trig values at this point, sine of 3 pi over 4. Now, because I know it's sine, and I'll throw cosine up here right now too, right? We need to find the derivative, which is just going to be plain old cosine of x. And so when I find our, put in the wrong value. When I find the derivative function evaluated at 3 pi over 4, you'll notice that these are linked, right? I need sine of 3 pi over 4 and cosine of 3 pi over 4. I may sketch a quick triangle, or maybe I do it in my head, right? 1, 2, is 3 pi over 4. And then the way I do my trig values, I say, okay, I know that's 45 degrees. Those are my pi over 4s. 45-degree triangle is x root 2. And we think of directions. As you move to the left, that's a negative x value. As you move up, that's a positive, and then the hypotenuse is always positive. So when I'm thinking sine, I think SOHCAHTOA. Let's see, sine, opposite over hypotenuse, x over x root 2. which is going to be just 1 over root 2. Now, I imagine most of you would prefer to rationalize that, and you'd call it root 2 over 2. The AP exam doesn't care which one you use, though. Okay. And then let's go ahead and do cosine of 3 pi over 4. Cosine, so kind of adjacent over hypotenuse, negative x over x root 2. So negative 1 over root 2, or for you purists, negative root 2 over 2. Okay, let's fill them in. We have the y value, and we have the slope. Looking pretty good. Now, you might look at that tangent line and go, those numbers are gross. There's no way that that's right. But a lot of times when you're doing practice, and we are just practicing at this point, you can pull in that technology to see if you're right or not. And so the way you do it is you take the original function, sine of x, and you graph it. And I'm just going to show you on Desmos really quickly. Maybe not. Hopefully this will fix itself at some point. So all you do is you graph sine of x on Desmos, and then you go through, now it's trying to wake up, and you graph the tangent line as well, and you just kind of visually check and you say, okay, well, is that the right graph? And hopefully the answer is yes. There we go. We'll just do it this way. Okay, so we have our graph of sine of x. I also put the point we found, 3 pi over 4 comma root 2 over 2, and you can see that it pops up on your graph. Now, if I turn the tangent line on over here, I'm expecting to see it kind of go through and just skim off the tangent line, or off the sine graph there, and it does. That looks pretty darn good. Right, so if anyone asked you, what is the slope or the derivative of sine at 3 pi over 4? Well, we now know the derivative of sine is negative root 2 over 2. All right, so now that we got how to check to see if your tangent line is right out of the way, let's look at 2 more of these. I picked these last 2 because I thought they were kind of some fun derivatives and you might end up with some interesting results. So let's look at 3. Right, the equation of the line tangent, blah, blah, blah. I mean, all of them are pretty much going to say the same thing. So we know we're going to go through. We'll have a couple blanks. It's at x equals 0, nothing too bad. And we'll do the usual. So the first thing we'll find is we'll find g of 0. Natural log of 0 plus e to the x. Nope, plus e to the 0th. Awkward. Let's see, we know that anything to the 0th is 1. And we should know that any log of 1 is 0. So I know this is going to end in a plus 0, or minus 0 if you want. Then we need our derivative, and this is really why I picked this problem. I like this derivative a lot. Some students are in the habit of saying, ooh, natural log, I know that, that's 1 over x. But the derivative of natural log is not 1 over x. I'd really encourage you to think about the derivative of natural log as 1 over whatever is inside. So the derivative of natural log is 1 over all the stuff that was inside. Now, knowing that, we also need to remember the chain rule. So the 1 over part is the natural log piece, but the chain rule is the derivative of everything that was inside. So here comes the chain rule. I'll tell that with the CR. Derivative of x is 1. That's a times right there. And e to the x is itself. However, you don't want to write it like that, because what that's actually telling us is that this plus e to the x, right? The multiplication is gluing the 1 to the rest. We do need to make sure there are parentheses there. And, of course, the cleaned up version would be 1 plus e to the x over x plus e to the x. Sometimes you'll even see the derivative of the natural log as what was inside is on the bottom, and then like an f prime on the top, or the derivative of the inside. So let's go ahead and actually find the derivative evaluated at 0. So 1 plus e to the 0th over 0 plus e to the 0th, right? So we end up with 1 plus 1 on top over 0 plus 1 for the denominator, which gives us 2. Therefore, our tangent line here is 2 times x minus 0 plus 0, which I bet a lot of you would just simplify to 2x. I also think it's pretty interesting that a pretty complicated looking function like this is actually just has a pretty nice tangent line of 2x. Okay, let's look at one more equation. Write the equation of the line tangent to x times e to the x at x equals 1. Well, first step, same as always. Let's find f of 1. That's just 1 times e to the first, which is just e to the first, or e. Now, sometimes students will get a little too clever here, and they'll say, I know E. E is 2.71828, whatever it might be. I would suggest you don't do that because E is not exactly equal to that. You've had to round the extra decimals out here. Just leave it as E. As soon as you start putting decimals in there and you're rounding, you're making your answers less accurate. The graders would absolutely prefer that you leave it as E and not just do an approximation. Plus, if you put the wrong approximation, you said it was 2.728, you'd lose the point because that's not true. So again, you can know E, that's awesome, but if you get E, keep it as it is. All right, let's find our derivative. So we take our derivative, f prime of x, and we just say it's 1 times e to the x, right? Or maybe not, because we should hopefully realize that x is multiplying by e to the x, which means we need the product rule. Now, for those of you that haven't watched my product rule video, I do teach it a little bit differently than other teachers, and I teach it this way because then it makes the quotient rule the exact same order. So for my product rule, I do the derivative of the first function first, keep the second the same. Then I keep the first function the same and do the derivative of the second, and the derivative of e to the x is itself. So if you switched where the x and the e and the 1 are, that's fine. It's the same thing. Some students will say, whoa, should we factor out e to the x here? If you want. Honestly, if I'm substituting numbers in, I tend not to simplify too much. I find if I do, then sometimes I can get into trouble. So what I mean is I'm just going to find f prime of 1 right away. It becomes 1 times e to the first plus 1 times e to the first. All right, or I have one of these e to the first plus another one of those e to the first. So I'm seeing 2 of those e to the first, or just 2e. So I think we've got our tangent line now. Our tangent line has the interesting slope of 2e. And I know some students will say, well, wait, how come there's two numbers there? Well, there isn't really. 2 times e, 2 times 2.7. We're looking at 5.4, 5.5, something like that, right? So this is one number. It's just written separately because they're not like terms. Right, at x equals 1, and then the y value we found, which was e. Right. All right, so we're on to the last page at this point. We've done enough examples with equations, so let's go ahead and look at the last couple. These last couple, I have graphs and then a table. So first one, figure below shows the graph of the function g and the line tangent to the graph of g. Maybe we should color coordinate this with the line tangent. That's this guy right here. Very nice. And then we also have the graph of g, which is this kind of cubic looking function, but we don't want to assume, so we'll just say this curvy looking function over here. There we go, nice. Okay. And their tangent at x equals -1. Let h be the function given by this. What's the value of h prime of -1? Now you might be looking at this going, oh, does this mean we want to write the equation of the tangent line of h? No. In fact, what they're actually asking for, in slightly different words, is they want the slope of the tangent line to h at x equals -1. Right? Because if you were writing the tangent line to h at x equals -1, then you would have h of -1 here and h prime of -1 here. They just want the value of h prime. They just want the slope of the tangent. They don't actually want the whole equation. In fact, if you gave them the whole equation, you'd be wrong. They just want the slope. So let's just go through that process. To find h prime of -1, the first step is we need to find h prime of x. You can't substitute -1 into an equation you don't have. So I see multiplication. Again, we have a product rule. Good thing we just practiced that. Like so. So we have e to the x is the derivative of e to the x. Keep the second one the same. First one the same. Derivative of the second. So the way we notate the derivative of g is, of course, g prime. Then we're going to find h prime of -1. So I'm trying to keep my colors consistent here. H prime of -1. So that'll be e to the negative first times g of -1 plus e to the negative first times g prime of -1. As we clean this up, we know e to the negative first is 1 over e to the positive first, right? To deal with negative exponents, we move them to the other side of the fraction, change the sign of the exponent. But then we have these last two, g of negative 1 and g prime of negative 1. Well, both of these should probably be blue because my g function up above is blue. So g of negative 1 means go to negative 1 on the g function. Oh, that's 3. So that's not too terrible. But what about g prime of negative 1? We need to remember what a prime or what a derivative is measuring about the original graph. If it had said, what is g prime of positive 1, they would want us to go to where positive 1 is on the graph and say, how steep is that? Well, at positive 1, that's certainly a positive slope, but I don't know, is it up 1 over 1, up 1 over 2, up 2 over 3? I don't know. Luckily, though, if we go to negative 1, which is where they're asking, right, at negative 1, they want to know how steep is it right here. But what's already measuring how steep that is? That's right, they gave you the tangent line, and the tangent line shares two components at the point of tangency. They share the y value, but they also share the same steepness. And as I mentioned earlier, it's pretty easy to find the steepness of a line. Just count. Down 1, 2, 3, 4, 5, 6. So we know it's down 6. And then to the right, the scaling on this is kind of weird. To the right, 1. And we're set. Right, so by finding the steepness of the green line, it also told us the steepness of the blue graph, though only for the point of tangency. And then we can finish this up a little bit, right? This will be 3 over e minus 6 over e. Common denominators, maybe negative 3 over e. Sounds great. Okay, let's try one more. Let y equals f of x be the graph below. Selected values of f of x shown. Looks like we'll have multiple functions, so let's do this one in red, like so. They also told us that f prime of 2 is negative 2. And then they say, cool, let g of x equal x times f of x. Write the equation of the line tangent to g at x equals 2. So let's put this down here. So we are looking for a tangent line of g at x equals 2, like so. That looks great. All right, well, let's find a few of these then. I think one of them we're going to need to find is, of course, g of 2. So we replace x with 2 and x with 2. So it's 2 times f of 2. Let's see, how do I find f of 2? Ooh, this is the graph of f. That's exciting. If this is the graph of f, let's just go over to 2, and there it is. All right, that's going to be negative 1. So it looks like g of 2 will be negative 2. Awesome. Okay, let's now look for g prime of x. Hopefully you figured out where this is going. X is multiplying by f of x. It's a type of derivative we've done before. I still did it wrong though. The derivative of x is 1. Keep f of x the same, and f prime of x. Nice. Then we need to find g prime of 2. So 1 times f of 2 plus 2 times f prime of 2. Okay, well, f of 2, we already found. F of 2 is negative 1. And then we have plus 2 times, and then f prime of 2. How do I figure out how steep it is there? Oh, but didn't they give us, they gave us that information at the top. The steepness, or the derivative at 2, is negative 2. Okay, so that'll be a negative 2. And so cleaning this up, or finishing it off, we have negative 1 minus 4, which looks like negative 5. Nice. And we have our tangent line. All right, the last problem that I have ready for you guys here, even though it is two problems, is built on this table down below. So let the table below have selected values of the continuous functions g of x and g prime of x. It's also known that f of 3 equals 2 and f prime of x equals x times cosine of e to the x. Oh my gosh, what a wild function. So let's start with the actual problem. They're giving us another function. Let k of x equals f times g. Okay, well, we know we got the product rule in here somewhere. So we've got our tangent line down below, And I think actually we're going to need quite a bit of room for this. Maybe I'll even drop one more space down below. And you're going to need a decent amount of space for the slope. Okay, and we know we're doing this at 3. Okay, so let's begin. We've got k of x up here. Let's start by finding k of 3. That's going to be f of 3 times g of 3. F of 3 is given to us. That's 2. And g of 3 isn't bad at all, right? We should know how to use a table at this point. G of 3 is negative 2. Cool. So we've got negative 4 for our y value. But now comes the slope. So let's start with k prime of x. Product rule, derivative of the first, keep the second the same, keep the first the same, and multiply it by the derivative of the second. Sweet. And now let's evaluate k prime at 3. So f prime of 3 times g of 3 plus f of 3 times g prime of 3. Nothing horrible so far. Now let's find each value. Okay, f prime of 3, they gave us the equation for f prime, so let's replace those. 3 times cosine of e cubed. G of 3 we can get from the table, we've seen it before, it's negative 2. F of 3 we saw before, that is 2. And g prime of 3 we can get from the table as well, that's negative 4. Now cleaning this up a little bit, we have 3 times negative 2 is negative 6 cosine of e cubed. And then 2 times negative 4, that's negative 8. So that's about as far as we can simplify without a calculator. And in fact, that is our slope. It's a number. You can do cosine of e cubed, multiply it by negative 6, and subtract 8. I don't know what number it is, but it's not really relevant because it is just our slope of our tangent line, right? It's going to be negative 6 cosine of e cubed minus 8. But if you write it like that, you will not get full points. Because what you've said right here is you've said the only thing multiplying by the x is the negative 8. Instead, to show that this entire slope is multiplying, we do need to put it in parentheses to show whatever that number is what's getting multiplied by the x minus 3. Okay, let's go ahead and try one more. Let h of x equal g of f of 2x. Write the equation of the tangent line to x equals 1.5. So we'll do one more tangent. Not sure how much space we'll need. And we'll have our x minus 1.5 right here. Okay, and we'll start with h of 1.5. H of 1.5 is g of f of 2 times 1.5. Now, please remember that this is not g times anything, right? We are composing functions. We're substituting one function into another. So we always start from the far inside. So it's g of f, and then 2 times 1.5 is 3. So I simplified the inside to 3. Now we find f of 3. So f of 3, ooh, we already knew that one. That's 2. And now that we found f of 3, now we can find g of 2, and g of 2, after all that, is 0. So my y value here is 0. Okay, let's find our derivative. Hopefully you're ready for this chain rule here, right? The derivative, the chain rule, we start on the outside and work our way in. It's really the opposite of what we just did on the previous problem. So we start with the outside function with this g, and we take its derivative, g prime. Derivatives only work one at a time, so I keep the f and the 2x exactly the same. Then we multiply by the next derivative, which will be f, so that's f prime. Keep the 2x the same again. Now we multiply by the next derivative. Derivative of 2x is 2. Okay, at this point in time, we've got our derivative. Let's go ahead and evaluate the derivative at 1.5. So g prime of f of 2 times 1.5 we did before, that's 3. 2 times 1.5, that's 3. And that at least saves us a little bit of time. Okay, so we have g prime of f of 3. We know that's 2. We've done that several times now. And we have f prime of 3. Oof, that was the gross one from before, right? That's 3 times the cosine of e cubed. And then we have a times 2. So continuing to clean this up, g prime of 2 is negative 3. So we have negative 3 times, and I'm going to go ahead and multiply these together. So times 6 cosine of e cubed. And hopefully you can see that negative 3 times 6 will give you negative 18 cosine of e cubed. Now we don't need an extra set of parentheses here because this is all multiplying, but if it makes you happy, you can throw that extra set in. And I think we're good for the day. You could, of course, left off the plus 0 too. So this is your either reminder or actual deep dive into learning what a tangent line is and how to write them. So hopefully you're feeling a lot more complicated on this, and either this is going to make your next test easier, or maybe you're here because you need to retake a test and you're ready to crush it. So thank you for hanging out with me. If I made any mistakes or if you have any questions, as always, just let me know, and I'm excited to have you back next time.